just had fun. 4 years ago, I was sitting there, and it was very enjoyable to be part of the operation. But I discovered I had so many ideas on how it could be done better that judging wasn't as much fun. So I decided to start competing. Not being very good at team building, every year I've been competing by myself. So the last 2 years I've been working on simplifying the design to the point where I can actually get close to completing it by the time the mission is ready to run. One of the things I decided was to think outside the box. Everybody's been having trouble with water leakage, penetrating into their electronics, their cameras, their other systems, and they're constantly putting RTV on top of RTV on top of RTV. So I took a step back and said, do we really have to? What works in water? And the first thing I thought was, well, you know, the motors are constantly making and breaking connections. Surely they won't work in water. So I took one of the little tiny electric motors with a propeller on it, put some long leads on it, dropped it into the sink, and it continued to churn and splash and make waves. So I thought, well, all right, it's not going to last for very long. So I kept trying it for a while, and I take it out and put it back in. I tried running over several decades, and it just kept on working. Well, the mission is 30 minutes. Now, yes, it would be nice to have one that would work in deep salt water, but realistically, the mission is a swimming pool. So if I design for the actual competition, I can simplify the tasks. So the next question, what else can go in? The camera. Camera goes in, camera goes dark. Well, of course, it's got all those sensitive electronics on the back that use very little current in order to process the video signals. So I cast it in acrylic, which is kind of hard to see here. Put it back in, and it gets blurry because the index of refraction in the front of the lens is different. But it continues to operate an hour or two later. Wow. Well, that only works in a measuring cup because the plastic housing on the front of the expensive cameras is not pressure covered. And the front surface of the camera is another very low current device. And even though pool water is nearly non-conductive, it is still somewhat conductive, which means the large currents are unaffected, but small ones are. So you need a pressure container for the front to protect the optics, to keep the surface itself dry. You need the back electronics to be protected, in which case I use the cast acrylic, and together it makes a single watertight, pressure-tight container that is quite small. And instead of using the standard connector, I bring 3 bare wires out so the water can't push between the wire and insulation. Cast it first, and then solder regular wires on it afterwards and a little bit heat shrink. Now it works fine in the bottom of the pool. Next, the LEDs. Well, the LEDs are high current devices. They really don't care if they're in the water. In fact, it helps them cool off. Then I tried the batteries. Batteries, left in the water for a little while, developed this brown ring of corrosion. Delphatic action. All right, batteries have got to stay out of the water. Microcontroller. As you can see, instead of putting all of the controls on the surface and a heavy tether, I prefer putting the power and the control processor on the ROV itself. I use an Atmel chip because that's my favorite. I'm going to try it with a microchip someday in order to support the sponsors. But the chip is designed to push or pull 20 milliamps out of every single pin. It's supposed to be able to drive LEDs directly. But 20 milliamps is very large compared to the conductivity of water. Therefore, it should also work. What it talks to are motor drivers. As long as the signal going in is okay, the signal coming out is about an amp to be able to move the motors. That shouldn't be a problem. Now, I have yet to actually get this thing running under surface control in deep water to verify that it really does operate wet. But as far as I can tell, batteries, camera, everything should be fine, fully immersed in water, as long as it is low conductivity water, for a while. The motors are not going to last as long as they would if they were fully sealed, but once again, for this specific mission, we can look at something a little bit simpler. So, in order to get full advantage, I designed my own printed circuit board. I did a special one for this year. Unfortunately, the prototype, which I made myself, suffered from handmade printed circuit board latest. I had too many fabrication errors, and I had to fall back to last year's pre-manufactured ones, which meant I didn't have enough drivers to run all the things I wanted to do. I'm going to see if I can multiplex some of the half-bridge motor drivers to run the laser and a motor in order to fire the torpedoes, which have yet to be implemented. I also have a gripper that uses parallelograms so that the faces move together apart, and then a circular drivetrain which is pushed by flexible steel bands that run up and down a threaded rod as the motor rotates. So it pushes the arms outward to cause it to extend, and then with tension pulls it back in again so you can get more force. And the faces always are parallel to each other, so it should be able to grip throughout the full range instead of just in one spot. That also is not quite yet done because I've been having trouble with my communications protocol. Last year, when I finally got last year's robot in the water, it worked up until the point that the communications went down. And the problem was that I was using that same 20 milliamp 0 to 5 volt CMOS to CMOS communication link from the bottom of the pool all the way to the top. And once it goes into the water, even 5 volts hydrolyzes water. And the varying rate of bubbles caused a little bit of static. And with such low-level signals, that swamped the actual communication. I lost contact and it just floated. So this year I'm using 485 bidirectional driver, which is much more robust, much more noise resistant. And hopefully I'll be able to take care of the problem, but I've yet to get into the pool to test that. So the basic design is A, to be very simple, easy to fabricate, so one person can get it done in time. B, to go for static stability, so we have a lot of buoyancy at the top and a lot of weight at the bottom. Since I'm using the batteries on the lower beam, I already have an obvious choice of weight to put in. Last year I used PVC for the flotation tank, and I discovered that PVC doesn't float very well. It has a specific gravity of 1.37. When you're using standard plumbing size, there's very little buoyancy left, even with all the water displaces. It weighs so much, and its couplings weigh so much, that it provides almost no buoyancy. Then I discovered that EVS has a specific gravity of 1.07, which means it's very nearly the same as the water displaces. It's almost no added weight. So all the air being displayed, all the air displacing water creates buoyancy, and also it doesn't come in a small size. So now I have nearly a kilogram of spare buoyancy. Because I have much larger tubes, it is sealed all the way up to here. There are bulkhead fittings inside here that I made. And this whole chamber here produced enough buoyancy, even with the batteries attached. But I had to attach quite a bit of lead to the front in order to get it neutrally buoyant. Which is nice because it's much easier to adjust for neutral buoyancy by adding weight than by adding a non-crushable flotation in small increments. So, in order to mount the motors, once again simplistically, the pipe extends a little bit more. I cut it in half and I get a little saddle. The motors are just taped in with black lipo tape. Once again, not good for years of operation, but very quick and eliminates the problem of zip ties, which have, even if you trim it properly, that nasty square box with all those nasty sharp edges, that after you've been working in the pool and your skin has gotten soft, very easily can cut your knuckles. avoid the zip ties throughout the entire assembly. And I only have two here that will be enclosed on the electrical board in order to stress relieve the tether right at the board itself, because those joints have a tendency to break when you flex them. So the motors, since I determined they didn't have to be sealed in watertight containers, I don't have to buy the expensive build pump pre-sealed cartridges. These are $1.50 DC motors. And if they fail, it's very expensive to replace. So that simplifies, once again, the operation quite a bit. The shaft was a bit larger than the size propeller that will easily work. These, of course, are high-speed, low torque. Therefore, you can't use a standard water propeller. You need something that has a very low pitch to it so that you can spin at high speed with low torque and develop as nice thrust without stalling out. So small aircraft propellers, which were too large to go onto the, or too small to go onto the shaft, and are putting on instead. The motors are driven by 3 quad half-bridge H-bridge motor drivers. And 2 halves of the quad come together such that you activate one on the low side, one on the high side, with a motor in between. Current flows in one direction. You then release them, the motor coasts. You activate the other pair, current flows in the opposite direction, and it goes backwards. That way you don't need to have a double voltage to be able to go forward or backward. And the microprocessor can send a very pulse width from 0 to 100% forward, 0 to 100% backwards, in order to vary the power. So that way I can move quickly to arrive at a position and then do fine adjustment in order to be able to align the gripper to grab whatever it needs to grab. The lighting comes from inexpensive Harbor Freight LED flashlights. You remove the aluminum and put 2 of them in series with water-cooled resistor in series to limit the current. I discovered that Harbor Freight makes them so cheaply because they rely on the AAA batteries being too weak to provide more current than what the diodes can handle. So when you put them on a much more powerful source, you have to put in a current limiter to make sure they don't go over current, burn up, and fail. The laser is mounted as close to the camera as possible, so that if I cannot see the illuminated dot against some object that just shines up into the sky, it will be close enough to along the side of the camera that the scattered light of the beam should still make a visible line. And then by lining up the line with the visible target, it should be possible to illuminate the buoy much more accurately than trying to bore sight of the camera or have an offset and try to figure parallax. Batteries are enclosed in Lexan, so I can see if there's any leakage. And they're enclosed with simple plumbing temporary caps, which means they can be removed and recharged normally. They don't have to be recharged in situ. Both wires come out the front side, so the back side is simply an end cap with a spring and one wire going up. The center part, I used a staple brad, so that I had a hole going through the center and then this big surface area that I could glue against. And then it acted as a button in the front of the long string of batteries. And in the back, it sprang out of the flashlight, so it was just like an oversized flashlight. And then a second wire coming through, and with the common problem of trying to go out of a pressurized compartment with a wire, my approach was to take a piece of ABS, wrap it up into a very tiny diameter tube, glue that onto the end or around the opening,